Hello everyone, here we have our research on predicting depression among students using machine learning algorithm. We chose this topic because student life can be overwhelming. Academic workload, financial stress, social expectation, and lifestyle changes often create pressure. Depression is one of the most common mental health issues among students, yet it is frequently overlooked. Early detection can make a significant difference, and this is where machine learning can play a valuable role. The main goal of our work is to explore whether we can use data-driven method to identify patterns linked to depression and predict students who may be at risk. More specifically, our objectives are to understand how different factors such as academics, lifestyle, and personal habit relate to depression. To apply machine learning algorithms to predict depression based on these factors, to compare the performance of these models and see which approach works better. In the rest of the presentation, we will walk you through our review of related work, our dataset and pre-processing step, the algorithms we used, our result, and finally our conclusions. Literature review. In recent years, machine learning has been widely applied in the prediction of mental health conditions, particularly depression. A number of studies highlight both the potential and the challenges in this area. For example, Priya et al. Used the DASS-21 scale to collect responses from 348 individuals and tested several algorithms. This study found random forest as the most effective method. Khadayat and Paudel, focusing on students, showed gradient boosting slightly outperforming other models. The work of Masood et al. Was groundbreaking, integrating classical ML, deep learning, and NLP transformer like Robert A. with explainable AI to identify key predictors such as anxiety and loneliness. This emphasis on interpretability is crucial. Another study on child depression used a large national survey and a random forest model to achieve 95% accuracy and identify socioeconomic risk factors. Innovation data use was showcased in paper 5, which employed passive smartphone sensing to predict depression onset week in advance with 85% accuracy. Model architecture evaluation was highlighted in paper 6 DDNet, a hyper ensemble that achieved near perfect accuracy 99% for student depression. Paper 8 provided a large-scale comparison, finding support vector machines SVM to be 99% accurate on DASS data, providing the best model is context-specific. This application extends to physical health. Paper 7 used over 4.3 million record to show gradient boost and random forest excelled at predicting hypertension risk, confirming non-clinical predictor. Finally, paper 9 demonstrated that machine learning can also forecast long-term hypertension control using AHR data, enabling proactive treatment adjustment. Overall, the literature confirmed that machine learning demonstrates significant potential to transform healthcare through ensemble methods like random forest and gradient boost, which consistently achieve high performance across mental and physical health prediction tasks. Our work builds upon these insights by focusing specifically on student-related factors, applying a range of machine learning algorithms, and comparing their performance to evaluate which approach is most effective in predicting depression among students.
For our research, we used the student depression dataset created by Shodu Lamu Opeyemi, a data scientist and machine learning engineer. The dataset is publicly available on Kaggle and is specifically designed for studying depression among students. The dataset contains 227,901 records with 18 attributes. Out of these, 8 are categorical features such as gender, city, profession, dietary habits, degree type, and family history of mental illness. The remaining attributes are numerical, including age, CGPA, sleep duration, and work or study hours. The most important column for us is the target variable, which is labeled as depression. This column indicates whether a student is classified as depressed or not, based on their responses. In addition, the dataset also includes several meaningful predictors related to academic and personal life, such as academic pressure, work pressure, financial stress, and study satisfaction. Together, these factors provide a comprehensive view of the of the academic and lifestyle challenges faced by students, making the dataset suitable for building predictive models. Before training our models, we carried out exploratory data analysis and pre-processing to ensure the dataset was clean and balanced. The first step was removing the ID column since it does not provide any useful information for prediction. Next, we examined the missing values. The only column with missing data was financial stress, which had just 3 null values, and because the number was very small, we decided to fill those values with the median, keeping the distribution consistent. After that, we explored our target variable, depression. Out of nearly 18,000 records, about 16,336 students were labeled as depressed, while 11,565 were not. This revealed a noticeable imbalance in the dataset, which could bias our models, which we also generated a correlation heat map to check how strongly different features were related to the target variable. Interestingly, none of these features showed a very strong correlation with depression, suggesting that depression is influenced by a complex combination of factors rather than a single dominant variable. Next, we focused on categorical features. Starting with the profession column, we found 31 cases with non-student values. Since this number was very small and irrelevant to our study, we removed those records. At that point, the dataset became exclusively student data, and we dropped the column entirely. Another major issue came from the city column. In addition to valid city names, the column also contained mislabeled entries such as degree names like MTech or MCOM, and even personal names such as Pabna or Vanya. To address this, we created a list of valid city names and labeled anything outside that list as other. For preparing the categorical features, we applied different encoding methods. Label encoding was used for binary features such as gender, suicidal thoughts, and family history of mental illness. One-hot encoding was used for city to account for multiple categories, and for ordered categories such as sleep duration, degree, and dietary habits, we used ordinal encoding. Finally, we applied SMOT, a resampling technique to balance the dataset. Before applying SMOT, the number of depressed students was 13,046 compared to only 9,250 non-depressed students. After resampling, both classes were perfectly balanced at 13,046 each. This step ensured that our models would not be biased toward predicting one class more frequently than the other.
For our study, we experimented with a range of machine learning algorithms to predict depression among students. We selected 7 different models representing both simple baseline approaches and more advanced ensemble methods. The models we used were decision tree, random forest, AdaBoost, logistic regression, k-nearest neighbors, naive Bayes, and XGBoost. Our approach to training was divided into 2 stages. In the first stage, we trained all models using their default parameters. This allowed us to establish a baseline and quickly evaluate how well each algorithm performs without any optimization. In the second stage, we applied hyperparameter tuning to improve performance. For this, we used techniques such as grid search and randomized search depending on the complexity of the model. Hyperparameter tuning was especially important for models like random forest, KNN, and XGBoost, where parameters such as the number of trees, maximum depth, number of neighbors, and the learning rate can significantly affect accuracy and generalization. The reason for choosing this diverse set of models was twofold. First, simpler models like logistic regression and naive Bayes serve as interpretable baselines. They are quick to train and provide a clear understanding of how features contribute to predictions. Second, more advanced ensemble methods like random forest, AdaBoost, and XGBoost are known to handle complex nonlinear relationships and generally achieve higher accuracy. Finally, models like k-nearest neighbors and decision tree help us compare performance across different algorithmic families. By training this variety of models, both with and without training, we were able to make a fair comparison and identify which approaches are best suited for predicting depression among students. Then, results and findings. After training and evaluating all 7 machine learning models, we observed clear differences in their ability to predict depression. Among the top performing models, AdaBoost, Logistic Regression, Random Forest, and XGBoost consistently delivered the best results. The tuned AdaBoost model emerged as the overall winner, achieving the highest accuracy of 85.02% and the highest F1 score of 0.8721, making it the most robust choice for this dataset. Logistic regression was also highly effective, showing identical strong performance in both its default and tuned versions, with an accuracy of 84.61% and an F1 score of 0.8673. Random Forest and XGBoost were very competitive as well, scoring accuracies around 84% and F1 scores near 87%, confirming the strength of ensemble methods in this context. Moving on to the moderately performing models, decision tree and k-nearest neighbors. They achieved decent results but lagged behind the top tier models. The decision tree benefited most from hyperparameter tuning, with its accuracy improving significantly from 77.72% to 81.72%, highlighting the importance of parameter optimization. Canon also shows a slight improvement with tuning, increasing its F1 score from 81.25% to 82.05%. Finally, Nibase was the lowest performer, with an accuracy around 78% and an F1 score of 81.55%, showing almost no improvement after tuning. Hyperparameter tuning had varied impacts across models. Some models like Decision Tree shows substantial improvement, like others such as AdaBoost, XGBoost, KNN, and Nibase only showed marginal gains. For logistic regression, performance remained unchanged, suggesting that its default settings were already optimal. Random forest shows a very slight decrease, which can occasionally happen if cross-validated parameters do not perfectly generalize to the test set. In conclusion, the tuned AdaBoost classifier stands out as the most accurate and reliable model for predicting student depression in this dataset. These results demonstrate that ensemble methods combined with careful hyperparameter tuning can effectively handle complex multifactorial data like the one we used. To conclude, our study demonstrates that machine learning can be an effective tool for predicting depression among students, with ensemble models like AdaBoost showing the strongest performance. Through careful preprocessing, feature encoding, and balancing the dataset, we were able to train reliable models that provide actionable insights into student mental health. We hope our work contributes to better understanding and early detecting of depression in academic settings, potentially supporting timely intervention and well-being initiatives. Thank you for your attention. Assalamu alaikum.